Swayam Prabha. Digital India. Educated India.
This is equation 2. So now, as you can see, this also represents a signal flow graph like structure. So let me draw the whole signal flow graph with now these two additional equations. So the basic signal flow graph diagram that we had was like this. This is A1. Sorry, this is S12. This is S2. In the previous diagram also the same thing has been done. Let's check. Yes, it's fine. Okay, so coming back to this one, this diagram. Now see these two equations, this A1, the contribution to A1, right? Contribution to A1, the sum of two values Bs and gamma S B1. So gamma S B1 represents this path, Bs the weight of 1 represents this path, and so A1 is the contribution of these two paths. So this is the, and this equation A2 equal to gamma L has been represented by this path. So a path is nothing but a line joining a source and a destination. Okay, the source is usually but not necessarily a independent node. Destination is a dependent node. Now, there are some other definitions like what is known as a forward path. So a forward path from any node to another node is a total path consisting of arrows in the same direction joining that point to another. So for example, between A1 and B1 there are two forward paths, these two. Okay, a loop is a closed path like this one. So you start from B2, you go to A2, and you can come back to B2. So this is a loop. Similarly, you have one more loop here, this one, and you have one more loop here, this one. So there are three loops in this signal flow graph diagram. Now, how do we find out the total? How do we find out the total gain or ratio? Okay, so for example, let us start with a simple circuit, like say we want to find out the input reflection coefficient. Okay, gamma in. Now, one thing I didn't mention is that in this above description, the characteristic impedance of both the ports was same and equal to Z0. That's why when we normalize it, we use this kind of expressions. Okay, so coming back to this diagram, this circuit diagram. So here I1 is the input current and A1 is the input normalized voltage, incident voltage. B1 is the input normalized reflected voltage. Similarly, at the output, B2 and B2 represent the normalized input and out incident and reflected waves. Incident and reflected voltage normal. Beg your pardon. A2 and B2 represent the normalized incident and reflected voltage waves. Okay, so the signal flow graph diagram of this circuit will be given like this. So we start with the four nodes, that is A1, B1, A2, B2. Okay, this is like this. Mm, like this. Okay. And we now have to find the ratio of, so gamma in is equal to B1 upon A1. So we first thing that we have to follow is how many forward paths are there. So forward path, as I said, one is this one and the other is this one. How many loops do we have? So I use the blue color for the loop. So this is one, there's only one loop. Now, in order to find this ratio, there's something called Mason's rule. So Mason's rule is given as the gain, if I represent by T, then that is equal to, now here Pk is the gain of the kth forward path. So in this case, for example, the gain of this path is nothing but, so P1. So there are two forward paths. So the gain is S11. The second forward path, it is S21 gamma L into S12. What is delta? Delta is given by this formula. Delta equal to 1 minus sum of individual loop gains plus sum of loop gains gain products of all possible combination of two non-touching loops, okay, minus the same, except that instead of 2 we have 3 plus the same, except that instead of 2 we have 4, and so on. Now what does this, first of all let's see what does this term mean. Sum of all individual loop gains. So first we identify all the loops and then sum of the loop gains. So for example, the loop gain of this loop is gamma L S22. Okay, if we had more than one loops, like for example in this signal flow graph that I showed before, you see there are two loops, this one and this one. So the gain for this loop is gamma S S11. For this it is gamma L S22, same as. So in our present circuit we don't have this one, we only have this one. So, and I just like to state one more thing, is one more loop, see this one. So there are actually three loops. Out of these three, this loop and this loop, they are non-touching loops. Okay, in our case for this circuit, if we go back, there is only one loop and there is no two non-touching loops. So had there been two non-touching loops, then it would be, we would have to multiply the gains of two loops taken at a time and then sum all those products. For this term, we would have to multiply the loop gains of three non-touching loops and then sum all those products and so on. So in this case, since we don't have this term, any term, this term is not present, this term is not present, this term is not present, only this term is present. So our delta becomes simply equal to 1 minus, there is only one loop gain, and that is equal to gamma L S22. Okay, so this is delta. Now delta K or delta 1 say is equal to delta not including loops which touch P1. So suppose we could, as I said, there are two forward paths, this one and this one. So delta 1 will be that value of delta obtained if we consider only loops that are not touching this path. So in this case, but in this circuit there is only one loop. This loop doesn't touch this path. Okay, this loop doesn't touch this path. Okay, so delta 1 is the same as delta, and that is equal to 1 minus S22 gamma L. But what about the second forward path? The second forward path goes like this. It does touch this loop. Okay, so this loop gain cannot be included in the expression for delta 2. Therefore delta 2 is simply equal to 1. Okay, now with these values established, let us find out gamma in, which is equal to P1 delta 1 plus P2 delta 2 upon delta. So P1 is nothing but S11, delta 1 is equal to 1 minus S22 gamma L plus P2. What is P2? P2 is this value, it is S21 S12 gamma L, and delta is 1 minus S22 gamma L. This is equal to S11 plus S12 gamma L S21 upon 1 minus S22 gamma L. Putting the value of gamma in. Okay, so that's how we find out the value of gamma in. We could have as well used an analytic technique for finding out gamma in, but it would be too lengthy, as you can see. So instead of that, this is a, as you can see, using this signal flow graph diagram, we obtained the value of gamma in much easily, because we had to understand what are deltas and forward path, but still, as is evident, this method was much simpler. Similarly, in the notes, you can find out some other examples, like finding out transmission coefficient T21 equal to B2 upon A1, and that comes out to be S21 upon 1 minus S22 gamma n. I am not doing this. I leave it as an exercise. It's given in the notes, so you can find it out. I will, I will just do this derivation for only one gain term, which is the power gain of GP. I will leave the derivation of GT and GA as an exercise given in the notes. So let us see how to derive the expression for GP and how this signal flow graph diagram makes it much easier. So GP equal is equal to PL upon P in. Let's redraw our two-port network. PL is the power delivered to the load. Okay. Gamma L is the load reflection coefficient. P in is the power entering the network. So I can write PL as equal to the magnitude of B2 square minus A2 square. P in, so here of course I have A1 and B1. P in is equal to A1 magnitude square minus B1 magnitude square. Okay, so then GP is equal to B2 square minus A2 square upon A1 square minus B1 square. Okay, now if I take B2 common from the numerator, B2 square common from the numerator, and A1 square common from the denominator, B2 by A1 modulus square into 1 minus A2 upon B2 square upon 1 minus B1 on A1 square. Now, does this term look familiar? I mean, this A2 upon B2. What is this A2 upon B2? If we go back to the equations we wrote a few minutes prior for a two-port network. So for this network, we call the relationship between A2 and B2. So A2 upon B2 is nothing but gamma L. This we can write as one minus modulus of gamma L square. And what is this quantity? We just found out. This is 1 minus modulus of gamma in magnitude square. Okay. Now, what is the value? So we have to find out the value of this quantity. Okay, so let us try to find it out. Let me draw the input network once again. So we have to find out B2 upon A1, right? How many forward paths are there between from A1 to B2? There is only one. So P1 is equal to S21. And how many loops are there? This one. Loop gain of this loop is S22 gamma L. And there are no further loops. So delta is equal to 1 minus S22 gamma L delta 1, because this is touching, because this path is touching this loop, so delta 1 will be simply equal to 1. So then B2 sorry, B2 upon A1 will be equal to P1 delta 1 upon delta, so that is equal to S21 and upon 1 minus S22 gamma L. That's it. And if we then substitute this value in this equation, what we get is like this. And this is the value of GP. So if you can evaluate this expression, we will get the value of GP. Now, what are some of the attributes of GP? Look, it depends on gamma L and gamma in, right? So it's like gamma in. Now, gamma in is a function, as you can see, of gamma L, isn't it? Why is gamma in a function of gamma L? Because we just a few minutes back we derived this expression, right? Gamma in is equal to S11 plus S12 gamma L S21 upon 1 minus S22 gamma L. So as you can see, gamma in itself is a function of gamma L. These S parameters are fixed for a particular two-port network. The only parameters that can vary is gamma L and gamma S. Okay. So now if we substitute this value of gamma n here, we see that GP also is completely a function of gamma L only. Now this is one advantage from a design point of view. It's like if you want to obtain a particular value of GP, then you just adjust the value of gamma L till you get the desired value of GP. However, the disadvantage is you are not taking into account the source impedance. Okay, so there is no part of the source impedance. So initially we one thing I didn't describe, which I should have at the beginning, is that suppose you have a two-port network. Say, why do we introduce the input matching network? So say let's go back to the basic two-port network with the source and a load. Okay, like this. Okay, so this is gamma in, this is gamma S, this is gamma out, and this is gamma L. Now maximum, the point of introducing an input matching network or an output matching network, say if your goal is maximum gain, then for maximum gain, achieving gain or maximum power transfer, we should have conjugate matching between say if Z in is the input impedance and Z out is the output impedance. For maximum power transfer, you should have Zs equal to Z in conjugate and ZL equal to Z out conjugate. Okay, or gamma S equal to gamma in conjugate and gamma L is equal to gamma out conjugate. Now try to prove this relationship, that when these two conditions are true, these two conditions will also be true. So you see, coming back to our design using GP, if you fix the value of GP to certain value, then you still have this input matching problem there. And to do that, say you fix the value of GP using a certain gamma L, then you calculate gamma in, and then you fix your gamma S equal to gamma in magnitude. So you see how simple the design becomes. All you have to do is fix the value of gamma L, find the value of GP, then find the value of gamma N and choose a gamma S that is equal to gamma N conjugate. Simple. But as I said, GP is based on parameters that we are not really that concerned. For example, the denominator of GP, the denominator of GP is P in, right? But P in is this value. P in is not a practical term. We don't really care about how much power is entering the input. So that's why, even though it's easy, in fact, the purpose of GP is to make the design easy. Um, uh, but then, in order to make the design easy by using some new definition of power gain, doesn't really solve the problem as such, because as I said, it has this term P in, which is not not concerned with our, as a user, we are not that concerned about what is the input power entering the network. We are only concerned about what is called PAVS at the input side and PL at the load side. Okay. Now let us consider the other gain term, which is the available gain. So GA, or the available power gain, GA now the GA is sort of the converse of GP, because if you just replace gamma L with gamma S and gamma in with gamma out, then you will get GA. So let me just draw the circuit diagram. So GA is given by PAVN on PAVS. So So you see that GA depends only on gamma out and gamma S, and you can, in the same way we obtained the expression for gamma in terms of as a function of gamma L. I would also like you to find an analogous expression for gamma out, which you will find is only dependent on gamma S. So in that way, GA is also only dependent on gamma S. So if you want to fix a certain value of GA, you just choose the value of gamma S, choose the value of gamma S, and you get that value of GA. Then find the value of gamma out, and then you choose a load which is equal to the conjugate of gamma out. So that's how the design happens. But then again, there is one problem with GA. It has this term PAVN, which is the power available from the network. So that's the maximum power that can be delivered to the load, not the actual power that is delivered to the load. And again, as a user, we are not that concerned with the power available from the network. We are concerned only with PL, the power actually delivered to the load. And that's why it's, even though it makes the design easy, it is not, it doesn't have a friendliness with the user. So that's one problem with this available power gain. And finally, let's see this the expression for transducer power gain. Once again, GT is equal to PL upon PAVS. PAVS represents the maximum power that a source can deliver, or the power rating of a source, and PL is the actual power delivered to the load, and they have a very good connection with the user because these are the quantities that actually matter. So again, I leave the derivation of the GT expression as an exercise. It is given in the notes. All these derivations are given in the notes and also in the book by Gonzalez. So for this active circuits, please refer to the book by Gonzalez. For the passive circuits, we are using mainly Pozar and then some parts of Rizzi. Now the expression for GT is given as these two expressions are analogous expressions. Analogous in the sense that here if you just replace gamma in with S11, S22 with gamma out, then the numerators are the same, okay, in both the cases. And I also leave it an exercise to show, for you to show that these two expressions are same. Now, the problem with GT is that it is a function of both gamma S. GT is a function of both gamma S and gamma L. This expression is, by the way, what we call the bilateral case. Bilateral case means this S21 is not equal to 0. Sorry, S12. Why S12 is significant equal to 0? That case is significant. I'll tell you in a moment. But for the bilateral case, S12 need not be 0. So then the problem that happens is, how do you design the gamma S and gamma L? See, if you want a particular value of GT, you can adjust the value of, say you keep the value of gamma L constant. Okay, say I have my gamma L, that is ZL constant. I adjust the value of ZS till I get a certain value of GT. Okay, then I find out what is gamma out. Fine. Okay, so I find out the value of gamma out after fixing ZS. But what will be my next step? Should I make gamma L equal to gamma out conjugate? Because if I do that, then gamma L first of all is dependent on gamma out, and if I change gamma L, then this GT also changes. Similarly, if I fix say the value of fix the value of gamma L, okay, um, and then I fix the value of gamma L for to obtain a particular value of GT. Then I find out gamma in and choose my gamma S equal to gamma in conjugate. That will again change the value. The moment I change gamma S, that will change the value of GT. So one way to do it is using an iterative procedure where we change gamma S and gamma L repeatedly till we obtain the correct value of GT. But that is not that convenient. Uh, there are some special cases, of course, as we shall see. One is the unilateral case. For the unilateral case, S12 magnitude is equal to 0, and then we shall see that this expression is somewhat easier to handle. Now, what is the significance of this statement that S12 equal to 0 magnitude? It is significant in the sense that power doesn't flow from output to input, which is true for many active devices. Or the the power flow from the output to the input is indeed very less for many active devices. Most of the power flows in the forward direction. For example, if you have a common source emitter like this, then power flows like this. Okay, so the power flowing back is very less. So that is true for many devices. This is true, and that's why this unilateral case is considered valid for many cases. And as we shall see, it does make the design much easier. Okay, so that was all I had for this part. We'll continue in the next part. Thank you. So, in the previous lecture, we introduced transducer gain. The expression for transducer gain GT is, I asked you to derive this expression. What we saw was that S parameter, this GT is a function of this S parameter matrix, and so value of gamma F and gamma F.